All right, so in this video, I'm just going to clear up the two definitions of infinite. One was that, let me write that out, so that non-finite sets are the same thing as Dedekind's definition of infinite sets. So that's what this video is about. All right, and so let me recall the two different definitions. So non-finite. So finite was that that they're equivalent to a finite set of natural numbers. So S is going to be our set. S is not in bijection with n sub n. And then, so Dedekind's definition of infinite set was that, so S is in bijection with a proper subset of itself. Okay, so okay, and so the goal, I mean, as stated, is to show that non-finite, so that it's not one of these n-element sets, is the same thing as the Dedekind infinite. Okay, and so to do this, we're going to use like a Hilbert Hotel type argument. Okay, so so let's get going with this. Okay, so let's first recall. Okay, so what am I going to do? I'm going to prove a lemma, and this lemma is going to require the axiom of choice. So let me start the lemma. Okay, so the lemma. And then I'll recall the axiom of choice. So every non-finite set has a countably infinite subset. So countably infinite means it's in bijection with the natural numbers. Okay, and so let's recall the axiom of choice real quick, because this is what we're going to use to do this. So the axiom of choice says that for every indexed family of sets, AI for I and I, there exists a choice function. So you're able to pick out a single element from this collection, a choice function. F from I into the union of the AIs. So there exists a choice, and this is a choice function is what I'm going to define here. This is what it is. Well, such that f of I is in AI for each I and I. Okay, and then a special case of this is when we can pick out, so a special case is that we can pick out elements in a power set. So I is equal to the power set of some set S. Okay, and so here, if B is a subset of S, so that B is in I, so then A sub B is just B. Okay, so in here, F is a map from the power set of S to the set S itself, and F of B is an element of B. Okay, so what it does is it picks out, so this picks out picks out one element from every subset. So I guess what I should say is this is the subset, and then you have to remove the empty set. Okay, so the set of the empty set. Okay, so so because if you want this to be true, you need this to be true, and so you need it to be non-empty. Okay, all right. So now we're going to so now that we're experts on the axiom of choice, we're going to apply that to this this particular problem here. Okay. Okay. So here's the proof that every non-finite set has a countably infinite subset. All right. So here, so we're gonna let we pick a choice function. Here, then we'll call it G, and it goes from the power set of S. So S is going to be our non-finite set, and then we remove the empty set to S, which is the union of all the sets. So remember, S is the union of all its subsets, so this looks like a choice function. Okay, and then the choice function has the property that if you take a subset, so for every subset of S, G of B is an element of B. G of like big B is an element of B. Okay, and so what we're going to do is we define. Okay, we have to use that S is not finite, so we define. And I'm just going to write down the function, and then I'll explain a little bit. So f of f. Okay, from the natural numbers to S. Okay, which is injective. Let me get rid of this. So natural numbers to S, which is injective. Okay, and f of the natural numbers. So the image of this thing will be our desired set. Okay, and so let me describe how this. Let me just write it down, and then I'll describe a little bit. Okay, so let me describe what this is. So for n is equal to 0, it's going to be this, and then so what we're going to do is we're going to remove the previous values. Okay, so we're going to do n minus 1 like so. Okay, n greater than, all right, let's do n is equal to 1. Let's do, okay, so we're doing with ones. So 1 here, n minus 1, n greater than 1. Okay, and so so this thing has here are the first couple terms. First couple values. So f of 1 is just we apply the choice function to the whole set. F of 2 is we apply the choice function to this, but now we remove what f of 1 was, so we get a different subset. Okay, and then f of 3 was we remove, so I'll write it here, g of s, and then we remove f of 1 and f of 2. Okay, so every time we're removing the previous values so that it'll be distinct. Okay, so all right. Okay, so since so let's make some observations. Okay, so now I claim that this performs as advertised. Okay, so the first thing is that since S is not finite, this thing will be non-empty. F1. This is not empty for every n. Okay, so we're never going to be able to do this, okay? And then now I claim that it's injective, okay? Okay, so we're going to let n and m be natural numbers, and we'll suppose that one's bigger than the other, okay? So by definition, what do we have? So by definition, f of m, right? This is an element of the previous value. So it's one of these. It's m is one number between 1 and n. So it's f of 2. It's one of these things up to n minus 1, because we know that it's a strict inequality there. Okay, but by construction, the next term, f of n, so this is an element of, remember, it's the choice function here. And choice functions have the property that, this guy is an element of here. And so so this is our g here. Our g does this thing. Okay? So it's an element of this. It's exactly where the FMs aren't. Okay? So FM is in this crap. F1, sorry. FM is in this stuff, and Fn is in the complement of that stuff. So it is impossible. So let me just say this. So it is impossible for Fn to equal to Fm. All right, and that proves that there's a countable. So we have a map from the natural numbers to S, and it's injective. Okay, and it depends on the axiom of choice. All right, so now we've shown that if we have a non-finite set, then we have this countably infinite subset. Okay, now using this countably infinite subset, we're going to prove we're going to go back to our main goal. And what's our main goal? To show that a non-finite set is the same thing as Dedekind's infinite set. So the theorem that I want to prove now, which is our goal, okay, is show that T is not finite if and only if T is equivalent, or by equivalent, I mean in bijection with, to a proper subset of itself. All right, so let's do the proof. Okay, and so the proof idea. Let me just say what the proof idea is. So I mentioned in a previous thing that there is an idea that is generalizable, and this was like this Hilbert hotel thing, and I believe I showed this that that I showed that the closed interval 0, 1 was in bijection with the open interval 0, 1. Okay, and this is where we showed that the power set of the natural numbers had the same cardinality as the real numbers. So we're going to use this same idea where we take this countably infinite set and we're going to shift it all down to make room for a proper subset. Okay, but the first part comes from a pigeonhole principle and a contrapositive. Okay, so we have two things to show. So we're going to show that, so this was the Dedekind definition. Let me just mark this here. So this was the Dedekind definition of infinite. Okay, and so let's do this one. So Dedekind implies T not finite. Okay. Oh, sorry. Sorry. The proof idea was Hilbert. Okay, let me clean this up. Okay, so let me just be more clear. The proof idea. This is a Hilbert hotel thing. That's the hard part. Hotel plus pigeonhole. Okay. Okay, so that's the motto if you ever forget what the thing is. So the actual proof is two parts. Okay, and so let's do the Dedekind infinite implies not finite. Okay, so this is half of the thing. So by the contrapositive, we can show that so that if t finite so contrapositive is when you take p implies q is equivalent to not q implies not p. Okay, so t finite is not finite implies t not equivalent to a proper subset of itself. Okay, and so this is exactly the pigeonhole principle. All right, and let's do the other way. So let's do t not finite implies Dedekind's definition. Of t infinite. That is equivalent to a proper subset of itself. All right. So this uses the Hilbert Hotel. Okay. So by the lemma that every infinite set or that every non-finite set. So we're trying to distinguish between non-finite and infinite here, and I mean non-finite. So by the lemma, every non-finite set is has some subset f from n to s. Okay, n to t. We're using t's, I guess, right now, which is an injection. The image of this map is the countably infinite subset that's guaranteed by the non-finiteness of the set. And that's the thing where we use the axiom of choice to produce that. Okay, so we have this injection. Okay, so the idea, so let me draw the picture. Okay, so here is this whole thing, this line is maybe t, and then what I've drawn here is f1, f2, f3, f4, and so on, right? And so what I'm going to do is I'm going to make it a bijection from t to itself. And what I'm going to do is for points that aren't one of these in this image of f, I'm just going to map it to itself and do nothing. So do nothing off here. So it's going to be the identity. And then we're going to do the Hilbert Hotel thing where we're going to shift everything on the image of the natural numbers. Okay, so we're going to do this successor function. Okay, so more precisely, we're going to define, so we define H, the Hilbert Hotel trick from t to t via in the following way. H of x is going to be, well, it's going to be f of n plus 1 if x is equal to f of n for for some n a natural number. So that's saying that that we landed on one of these guys, okay? And then when we land on one of these guys, we shift. Otherwise, we're going to take it to be x, so it's just going to be identity if it's not in one of those things. Okay, and so you can check that this is an injection, so we just shifted this injection, that's fine. And then what's going to happen is that this is a proper subset of itself because we've F1 is no longer going to be in the image. All right, so H is a bijection from T to a proper of itself. Okay, so this clears up now. That's it. And this is how we show that these two definitions are equivalent. Okay, so let me just recap again. What we did is that we showed that for every non-finite set, we can produce a countably infinite subset. And then using that, we did this kind of Hilbert Hotel trick, right, to shift this countably infinite subset over, and this produces a bijection to a proper subset. All right, so that's all I have to say about that. Leave some questions in the comments.